Hello and welcome to today's Wolfram Institute live stream. Today we have Gabriel Leuenberger coming to us from Europe, and Gabriel has a lot of interest in computation, philosophy, and science, physics. Today he'll be talking about a general proof, mathematical proof for Occam's razor. And Gabriel, take it away.
Thank you for having me, Dugan. I'll start by explaining the title of this presentation. So it mentions theoretical physicists. So you might think I will introduce a new physics theory, but that's not what I'm going to do. I'm going to do something more interesting, which is to introduce some new methodology for the physicists, which would address the root cause of the stagnation of their field. I'm also going to explain what the root cause is there. And this has something to do with Occam's razor, but not just the old, purely philosophical principle of Occam's razor, but modernized, mathematicized version of Occam's razor. And I'm also going to talk about why this is true and why it is highly effective to use this new methodology. And this is highly general. What does general mean here? It means this applies to all kinds of different models, scientific models like deterministic models, stochastic, randomized, probabilistic, quantum, classical, rewriting systems, whatever, all kinds of different models, yes. So I'll start. Here is the outline. I will start with the history of Occam's razor briefly, then I will talk about how to define the complexity of a model, because if we want to apply Occam's razor correctly, then we need to have some objective definition of how complex a model is, right? And then I will give an overview of the general mathematical proof of Occam's razor, and then I will, at the end, maybe is the most interesting part where I get into physics and all of that. And I was told in the past by some people that they have listened to me as if it was a podcast while riding the bicycle. I would not recommend that because I have many slides that you can look at. So yeah, okay. The history, let's go back to ancient Greece. This is the painting by the School of Athens by Raphael. In the center, you can see Aristotle. The reason he's at the center is because he was actually a central figure back then that influenced many different fields, like also started these fields or engaged in these fields: biology, metaphysics, linguistics, geography, politics. He invented logic, did astronomy, and so on and so forth. And the reason I'm mentioning him is simply because he actually invented Occam's razor long before Occam. And there's the reference down there where you can see that. And now we jump forward, literally ages forward to the late medieval times, where actually William of Occam lived, after whom Occam's razor is named, obviously. And Occam is the town where he's from. And down here you can see the most common formulation, which is "thou shalt not multiply entities beyond necessity." And he was a scholastic, and this arrow here from scholasticism to modern science, that essentially represents the scientific revolution. And if you think of someone else who also comes from around London and has something to do with the scientific revolution, of course, that's Isaac Newton. Isaac Newton, in a time when people believed, had all kinds of superstition, and science was really not very advanced. He invented all kinds of, figured out many remarkable things. My favorite is the mirror telescope, but there's, of course, much more here. And what's the secret behind his great success? You can find it in his book. Actually, it's multiple books, but there's one book that contains a bunch of rules. Here, rule number 1 in his book is actually Occam's razor, and you can see that there are two different formulations. Actually, the first one is really Occam's razor, and the second one is a slightly more strong statement about that the universe should be simple, basically. Are you guys still here? Am I actually, is everything fine? Can you hear me?
Yeah, so everything's going smoothly.
Okay, good. So if I talk about Isaac Newton, of course, I have to also talk about Einstein, because people will inevitably ask me questions about Einstein. What did he think about Occam's razor? And for this, I have an interesting story for you about Einstein and Occam's razor. So there was a time when he completely ignored Occam's razor, and it actually was quite detrimental to him. It wasted 3 years of his life, and he published some false versions of general relativity initially. And then towards the end of these 3 years, he became desperate because other scholars, mathematicians, they were catching up to him. So he would have lost priority on his own work. So therefore, he then, in desperation, accepted Occam's razor, and then he sped up his work so much that he published the correct version within 2 months. And I didn't just invent this story. I mean, you can find it in this paper down here if you want more details on this. And after that, Einstein actually explicitly praised Occam's razor many times. He didn't call it Occam's razor. Back then, it wasn't really called Occam's razor, actually, or it wasn't famous under that name. So, but anyways, here are the quotes. So there are many. I'm not going to go through all of them. In yellow, you can usually see that it's always about something with simplicity. And here at the end, he does mention that he believes that simplicity is the key to making much more progress in physics and all that. And also, I didn't just AI generate these quotes. Of course, down here is the reference to the book that contains all of these quotes. Here is Occam's razor again. And now, what does this stuff even mean? Almost everything about it is actually unclear. So here, what entities shall we not multiply? It's not clear. Why should we not do that? It's not really clear either. And then how do you even count objectively how many entities you have? Because it depends. You can like set up a model in a different way, and then the count might be different. And then unnecessarily or beyond necessity, it's not even clear what that means either, because necessity is also a matter of degree. So we need to quantify that also. And I will get to all of these, but yeah, first it's gonna, yeah, later in the presentation, I'll get to this. So we want to mathematicize Occam's razor, which is in the realm of philosophy of science, and then move it into science of science, which is meta science. And that will be less vague and more useful, therefore. And here, there's also a history. We're still in the history section, actually. There are a bunch of failed proofs. There were some failed proofs. For example, they tried to use Bayes' theorem alone without further help to prove Occam's razor, and that has failed repeatedly. Actually, you can see it here in this reference where they have repeatedly, where they have, where this occur. That's kind of a small collection of these failed proofs. And then similarly, also for PAC learning, PAC is probably approximately correct learning theory. There also have been proofs that were debunked and things like that. Yeah. So, but note that they didn't use Kolmogorov complexity, and that's the reason. I mean, there's nothing wrong with Bayes' theorem per se. There's nothing wrong with PAC learning either per se. But because they didn't because they didn't use Kolmogorov complexity, it led them to fail repeatedly with these attempts. Yes. Everything still okay?
Yeah.
Okay.
Yeah, so we have a question. James is asking about Einstein. How did he use Occam's razor? How did he get those results after 3 years of failure?
Basically, he already had the results at the beginning of these 3 years. These were together with some mathematicians. He figured out the right kind of equations. And then after that, he was somehow not satisfied and just continued making it more complicated. And he became lost in math, kind of like Sabine Hossenfelder's book, the title of that book, right? Lost in Math. So he stagnated for 3 years. And then, yeah, he just, after all this time, he just went back to the simpler solution that he actually already had ready in the beginning, that is somehow ignored for some reason. Yeah. But for details, you can just look at the reference that is on that slide, at the bottom of that slide. Yeah. And shall I continue?
Yeah, I have a question on
Yeah,
this slide. What is pack learning?
Probably approximately correct learning.
I see.
That's like a small subfield of machine learning, of the field of machine learning.
Mm.
Yeah. And they also have these, Occam's razor arguments. Okay. So then we come to Solomonov's universal induction, which actually, he did actually mathematicize Occam's razor, how to use it correctly. But this was not a proof of Occam's razor. It didn't have a convincing argument for why this is really true. And was also not quite so objective and all that. So, yeah, that's in the 1960s, that's still history. And so since then, there were many improvements, and but it has never been widely accepted. This has never been widely known that there exists. I mean, there have the mathematics has actually been developed to some extent, to a sufficient extent, I would say, to prove Occam's razor, but this was so poorly explained, basically, that it never spread into, for example, a field like physics. So they actually don't know how Occam's razor works, or how modernized, the state-of-the-art kind of Occam's razor to epistemology and meta science. Okay. And now come to model complexity. Scientific models as algorithms, and algorithm is the name of comes from this guy that lived a long time ago. Um, Objectivity, reproducibility, falsifiability. That's how scientific models should be. They should be clear enough such that you cannot manipulate them to circumvent falsification. And yeah, that means they should be clear instructions that give you some predictions, or at least you should be able, from the model, you should be able to derive predictions somehow if they don't give you predictions directly. And yeah, clear instructions, which is basically what algorithm refers to. It is widely known that this can be always be automated by a Turing machine. This is the Church-Turing thesis, which is a consensus among computer scientists. And there is such a thing as a universal Turing machine that can emulate every other possible Turing machine if you give it the right program. And you can also make a one-to-one correspondence between all possible scientific models and all possible computer programs. This is if you want it to be fully general. So anything goes as a scientific model. Any program you can view as a scientific model of some sort, as a model of some sort. And remember that the old failed proofs, they were just not the one-to-one correspondence. You can just identify them with each other. Okay. And then there's theory and a model. These are not quite the same. Oftentimes these terms are conflated, but theory is more of a cluster of models, also with theorems about these models, and models can also contain other models and stuff like that. So they are not, theories are not really, it's not the same. It doesn't mean the same. And also, with regards to Occam's razor, if you develop a simple model, and this model might be part of a more complicated theory, and then, for example, you make a presentation and you present your simple model, you say, my theory is simple, and therefore it's true, or something like that, then it might lead to misunderstandings. People might think that it is not simple, but actually, so because it isn't, because the theory is not so simple, but your model actually is simple. So then, yeah, it might be rejected even though it was actually simple. Yeah.
Okay, so a
So
model is
maybe
basically like the base unit in this. It's the smallest thing that describes a phenomenon,
yeah, you could say that. Yeah.
I guess, and like a theory
And
could be an amalgamation, a combination of different phenomena that are interacting.
yeah, yeah, exactly. And also maybe not even different, it could be the same phenomena, but you still have like a collection of different models that somehow explain this. Yeah, sure. Uh, and then for measuring how complicated a model is, we need a reference formalism. What is that? That's basically a language. So the objective definition, like it says here, of model complexity should be the size of the program that corresponds to that, but in which language? And this is an old problem. How do you select this objectively somehow? And Kolmogorov called this the description language, and this was also called reference machine and reference language, reference computer, description method, etc. There are many in this discussion about which one to choose. There are many of these. This was discussed many times actually. All of these terms, they refer to the same idea by different people. And then which term should I use? And I decided on this term, which is another term from all these other ones, but this is the only one that made sense in the end. So the question is, well, which reference formalism should we choose? And there's this claim in general by various people that the reference formalism is supposed to be simple, but I will, and this claim, this leads to some confusion generally. I'll get to that. There are some objections about that usually. So firstly, how could we possibly select the least complex reference formalism if the definition of complexity already depends on the choice of a reference formalism? And then secondly, if we postulate that the reference formalism ought to be as simple as possible, did we not just invoke Occam's razor, and therefore any proof of Occam's razor derived therefrom would consist in a fallacy of circular reasoning? And the first one is more about circular definition, and the second one about circular logic. So, and these two different objections, because both of them contain some kind of circularity, they can easily get conflated with each other, right? So people might not know that these are two different objections, and then it will confuse them even more. So you can like clearly distinguish the two, and then you get less confused. Is everyone still here? I'm just, because I never hear anything, I'm just checking. Okay. So there was one attempt to resolve this issue, these two objections, by considering all possible reference formalisms and then looking at how they relate to each other, how easily they can simulate each other and things like that. So it's a little bit sophisticated here, but Markus Müller himself, the one who proposes, he proved that this is never going to work. You cannot get it to be completely independent. So he didn't want to choose a simple reference formalism. He wanted to do something else that is somehow more objective, that where you don't need to make that choice initially. But then he himself proved that this is impossible. And yeah, that's also useful to have some kind of negative results. So I will move on now. But then what are the resolutions here? For the first one, I will say that the solution is basically just that there exists reference formalism that is extremely simple, that is remarkably simple, untyped lambda calculus. And for the second one, well, it's not circular logic necessarily, because it ought to be simple for a reason different from Occam's razor, and that reason is here. If you would allow for complicated reference formalisms, you could abuse that to take some complex model and pretend like that is simple. So for instance, if someone wants to claim that their model is simple, they could just, if we allow for complicated reference models, reference formalisms, they could just build in the subroutines necessary. So for instance, if I would have a theory that consists of linear algebra, I could say my reference formalism is MATLAB, and in MATLAB, my model is very simple, right? Because because matrix multiplications are, for example, they are just a couple of symbols, so it's very, I can make it very short, but actually, really, it's much more complicated behind. It's only superficially simple, and behind that, there's a bunch of hidden complexity there, and that would be kind of cheat code. That would be fraudulent, and we don't want to allow that. So that's, you can argue like that the reference formalism should be as simple as possible, so no extra information can be sneaked in. Yeah.
Right, I
And
see. So it's like the complexity of the subroutines that you're invoking, for instance. Like, you could write
yeah, it
a
should be as small
one-liner
as possible.
program and it's like, oh, this is a simple program, but the functions you're calling are like in themselves very complex.
Yeah, yeah. And we
So,
don't want to allow that, right? So
okay,
that's why
so
the
yeah.
reference formalism needs to be, yeah, simple as possible. And the untyped lambda calculus is just that.
Hmm.
Uh, yeah, now the lambda calculus, it's quite old and also famous, widely known, widely used. It's also an ancestor of some modern languages, and also it appears within C++ and Python and all that. Um, Yeah, I think every computer scientist actually knows what lambda calculus is, but most physicists don't know what it is. And also, actually, Lisp that I mentioned here, the language Lisp, invented by John McCarthy, it was also suggested by Solomonov originally that this should be the reference formalism. And also Gregory Chaitin actually used it as the reference formalism at some point. But, well, lambda calculus is the ancestor of that, and it's simpler. So let's just go back to lambda calculus. Although there is a little problem with that, which I will mention, but it's not a real problem. Um, yeah, it's the untyped lambda calculus is so simple that it will astonish people because it's like as simple as Euler's. It's kind of similarly baffling to Euler's identity, I would say, when people first learn that this is actually computationally universal, because it consists of basically just one um, operation, which is just cut and paste. And is because you had someone presenting something about how simple Boolean logic is. Is Boolean logic simpler than this? Simple Boolean logic, perhaps, yes, but it's not computationally universal. To make it universal, you would have to add to it, like you'd have to upgrade it to predicate logic, and then you have to add set theory, or you have to make it into higher order logic. So it's actually not simpler at all. These logic systems, they usually also have a whole bunch more rewriting rules than just one rewriting rule, like the lambda calculus. And so I would say, yeah, that should definitely be the reference formalism. But then the little problem is here that, well, all of algorithmic information theory, so this whole theory about Solomonov induction and Kolmogorov complexity and all that, that's all formulated in terms of binary codes and Turing machines. But that has already been resolved by John Tromp, who developed the binary lambda calculus. So all of this is not a problem. You can see it in this paper down here. This is the reference. And he also compared it to some other alternative possibilities, like, for instance, SK calculus, which is also a very simple reference formalism, but it's not well suited, according to him, as a reference formalism at all, because it's not so expressive, it's less powerful. Yeah, I will just continue here. I could say, oh yeah, maybe another comment, because this is for the Wolfram Institute. You can also argue, there's another argument for lambda calculus over Turing machines, which is similar to the reason why, for instance, Stephen Wolfram, who used to talk always about cellular automata, and then he started to shift more toward hypergraph rewriting, which is that the former is totally ordered in time, so it's kind of more restricted. And then the second one is only partially ordered in time, so you can have something more like space-time. That's why Stephen Wolfram, for instance, wants to build space-time from hypergraph rewriting. And of course, also lambda calculus also allows that. It also has that flexibility. It's actually also only partially ordered in time. The steps of computation, they are only partially ordered in time, kind of like space-time, whereas yeah, many other models of computations are not like that. So that's another something else which is relevant here. And I will come to, yeah, back to hypergraphs later on also. Here is some stuff by John Trump, and he also has a nice talk. He had a nice long talk on YouTube once about his paper about the binary lambda calculus. And here are his diagrams animated. So these were invented by John Trump, but then animated by TwoSwap. So thank you for
Yeah, those are
thank you
nice.
TwoSwap. Yeah, thank you. They're kind of not running very fluently here. And these are just small examples of some Lambda programs that are looping and non-halting. And also TwoSwap made a nice video about all of this. And we are three different people. So John Trump, TwoSwap, and me, we are three different people. I will, yeah, thank you.
Yeah, so on the subject of
It's not the end of the
lambda
presentation,
calculus,
right?
it's
We are like halfway through or so, right?
yeah, I just wanted to mention that Stephen Wolfram just put out a blog today or yesterday on
Yeah,
lambda calculus.
yeah, it's pretty long. Yeah, I saw. I haven't had the time to read through it yet.
All right.
Do you want to comment on it or something? Or
I just wanted to make note.
okay. Next, general mathematical proof of that. I start with a bunch of initial assumptions. Of course, I cannot start from Occam's razor. I should make sure that Occam's razor is not in the initial assumptions. And then some famous computer scientist actually once proposed as an initial assumption to prove this, the great programmers, like some programmer that programmed the universe or something like this. But we don't need this. This is a bit too strong of a claim and all that, right? And then also the computability of the universe was also suggested by some people sometimes. And I would say that's not necessary. We don't need to postulate the computability of the universe. That would be kind of a strong metaphysical claim. This is not necessary. Instead, we can just use the following initial assumptions, reproducibility that of scientific models at least, because when I actually suggested reproducibility, some people already complained like not everything that science does has to be reproducible, but okay, at least the scientific models have to meet that standard themselves, right? So such that if you run a scientific model, it should give you the same. That's what I mentioned earlier about the algorithms, right? You should not be able to circumvent falsification and stuff like that, right? And the Church-Turing thesis is another initial assumptions, which I mentioned earlier, I think also, and then the full generality. And the lambda calculus is extremely simple. I mentioned all of these. And then another one is that an assumption of impartiality, neutrality, fairness, objectivity for science and epistemology. And this shows up sometimes as the principle of indifference or things like that. And or like, for example, when we said that the reference formalism should be as simple as possible, that was also, for instance, to avoid cheating in some way. So that's what this is all about. And these are all of the initial assumptions that I think there should be enough to prove Occam's razor. And I think everyone can agree with these initial assumptions. Yeah. So, and here, what also appears in the proof is Kolmogorov complexity. I'll just give a very brief summary of what that is. Kolmogorov complexity is just a very general measure of how much information is in bit string, for instance. And the science about Kolmogorov complexity is called algorithmic information theory. And this has in the past enabled the general mathematization of various concepts such as randomness, similarity, intelligence, thermodynamic entropy, aesthetics, and so forth. For instance, about randomness, there's a whole Wikipedia article just talking about Martin Löw randomness. So this general definition of randomness based on Kolmogorov complexity. And for example, for similarity, there's a paper called or there's this concept and some papers about it, universal similarity metric. And intelligence, for instance, there's this definition. by Shane Legg and Marcus Hutter. Shane Legg is like one of the founders of DeepMind. And he had this, there's this Shane Legg and Hutter universal intelligence measure. That's also a whole paper and all that. And yeah, about aesthetics, there's Jürgen Schmidhuber's paper about his definition of beauty and thermodynamic entropy. There's also papers about that. Yeah, so that's a whole field, and that is very generally, Kolmogorov complexity is quite generally useful. And now we will use it for proving Occam's razor. And the most commonly used version of Kolmogorov complexity is prefix-free Kolmogorov complexity, which is the size of the smallest possible self-delimiting program that will have returned only x upon halting. So the Kolmogorov complexity of x is the size of the smallest possible program that returns x. And this self-delimiting, this prefix-free Kolmogorov complexity was invented by, I think it was Gregory Chaitin. And yeah, it's called prefix because no self-delimiting program is a prefix of another self-delimiting program. Yeah. And now we come to the summary of the main argument for why Occam's razor is true, actually. This is kind of a frequentist approach, but you can also take a Bayesian, you can translate it all into a Bayesian approach. This is all fine. And yeah, the models are basically, I make an analogy to politics. I am not interested in politics at all, but I think it is easiest to understand like this. So the models are the voters and the past observations are the jurisdiction. What this means is just that the models that we consider here, they should agree with our past observations. And then the predictions are the candidates basically, and the models vote for these candidates. The models, they make some predictions, right? And this arrow, this last arrow here, you can think of this as Solomonov induction essentially. And now we maximize the charitability toward high model complexity. So we let the complexity go toward infinity. So it's going to be a large set of arbitrarily complex models. And what comes out of this remarkably is actually that this democracy, the democratic outcome of that, will agree with the simplest models. And there's a mathematical proof for that that holds in general. And that pretty much proves Occam's razor. And there's a whole bunch of people that have produced the mathematics that led up to this. So for instance, Leonid Levin, he invented the coding theorem, which was an important step a long time ago already. And then some other people also, well, advanced this. So that should prove Occam's razor. But the proof, it starts from, actually, I should probably skip all of these details here for this audience. It's probably not that interesting, but it uses a bunch of basically algorithmic information theory. That it uses the chain rule, which is analogous to Shannon's chain rule for entropy, a chain rule for Kolmogorov complexity. And yeah, I'm just skipping forward here. These are the theorems that build up toward that. And here are also the independent variables that are also part of this. They are given as an input to the models. And the result is this one. That's the important. This is the important result, which says that the probability ratio between two predictions, for instance, A and B, let's say you have a prediction A and a prediction B, and O here denotes the past observations, and Z is just the independent variables. They are optional. You can also leave them out, or yeah. And the ratio here, it will be ultimately given by the Kolmogorov complexities of A versus B, which you can see at the end of this equation. Are you still here?
Yeah. So the prefix is sort of a set of initial conditions that are being input into the model?
Yeah, basically you mean the independent variables, yeah.
Yeah.
They can be like that. They can be like initial conditions, yeah. Or like an experimental setup.
Or a set of a
That's what
logical
the
assumptions.
yeah, it could also be that. It's very general, yeah. It could be many different things actually, because there are many different kinds of models, yeah. There are actually whole books written just about like what's even a scientific model and stuff like that. So what's important here to note is that the probability ratio on this side, it depends on an exponential of a difference. There's a difference between Kolmogorov complexities. And well, if the difference is only, let's say, 30 bits, then that's already, because if you take 2 to the power of 30, this will already result in 1 billion. It immediately shifts the probability ratio very much to one side versus the other side. So you can immediately discard the more complex model. And that's what proves Occam's razor. And that's also what makes it highly effective, that this is that you immediately get orders of magnitudes from just relatively small differences in model complexity. Yeah. So that's the secret behind it. Now we get to physics.
Can I ask a quick question?
Yes.
So, so one thing that I'm still kind of searching for is the formulation of Occam's razor that sort of in some sense in my mind can be proven, right? And what you have on this page is sort of the statement, there's a secret behind the success of Occam's razor. And to me that that feels like what you're demonstrating here is more of a secret behind the success of Occam's razor rather than some sort of a proof of a theorem or a statement.
Yeah, I mean the proof
I,
is back here, but I kind of skipped over it. You can like it's in my paper basically all of these. I didn't want to get into all of this detail here because it's kind of the talk is kind of long.
Yeah, I guess what I'm searching for is the statement of Occam's razor in terms that, in my mind, can motivate a proof. Like I can certainly understand um, a demonstration of the secret behind the success of Occam's razor, but I'm still struggling to understand what the formulation of Occam's razor is that can be proven.
Oh, okay. Um, that would be take this take the simplest. So if you have a bunch of data, take the simplest, the shortest program that will generate that data. And then the probability that this is, well, basically it's here, it's the probability ratios, right? The probabilities, it's about, so prove Occam's razor, it just means prove that Occam's razor will increase your chance to get correct predictions, or it will maximize your chance of getting correct predictions, basically. So
Okay, that helps a lot. So the proof
yeah,
is that you should always pay. It's actually a suggestion. It's like a strategy.
yeah, exactly, yeah, it is.
Yeah.
So one has to prove that this strategy will lead to down the line, or yeah, that's the goal. The goal is getting to correct predictions, right? So that's
Yes.
the
So that this is an optimal strategy. So this is a proof of Occam's razor as an optimal strategy.
yes, yes.
Okay.
And at the beginning there we have basically the probability ratios between getting to between making the correct prediction if your prediction is A versus your prediction is B, right?
Thank
And
you.
then on the right side you have the Kolmogorov complexity, which is just the shortest possible program that will generate these predictions alongside the the old predictions. So O is like the old predictions, and the B is the new prediction, and OA is like the old predictions plus new prediction A. And yeah, so, and there the difference is difference in model complexity, basically. And then the exponential of that will give you this probability ratio, and then that shows you that this is a very strong strategy. Yeah. Now to fundamental physics. It seems like this contradicts Occam's razor, right? Because our universe it seems kind of complicated, but it doesn't actually contradict Occam's razor, first of all, because the Kolmogorov complexity of our universe might actually be quite small. Max Tegmark has pointed it out in some paper you can see here. And second, there's an independent reason. Well, actually, is Occam's razor strong enough to prove that our universe is simple? Not really. You can also see that Isaac Newton in the beginning of my talk actually had two different versions of Occam's razor, essentially a weaker one and a stronger one. And here it's only a proof of the weaker version. It doesn't prove here that the universe must be simple. It just, what it actually just proves, this mathematics here, and what Occam's razor basically says, is just that that's the best strategy, regardless of whether the universe is simple or not. The best strategy is simply if you go for the simplest, the strategy most likely to lead you to correct predictions is the one which is to get find the simplest models. Sorry for my stuttering here.
Right. So I guess like the universe doesn't have any obligation to be as simple as it should be, or
yeah, exactly,
as simple as it could be. It has stuff happening, that stuff is doing activities, phenomenon are occurring, and then what, we're trying to model those, trying to see what kind of computation that the universe is doing at these various scales, and then basically when trying to decide how to model it, the simplest models for a particular phenomenon are usually the more correct ones.
Yeah. Correct, yeah. And the math basically shows if you neglect Occam's razor, then you waste time on false models and then you fail. That's kind of like what happened to Einstein initially. It doesn't guarantee your success, but at least if you don't use it, you're guaranteed to fail. Yeah. Now there's the next question about physics, which is, does it contradict the many worlds interpretation? Because some people think that the many worlds interpretation is too crazy and it contradicts Occam's razor and all that. But what I'm telling you here is that basically there is no such problem, because what matters is not that it uses a huge amount of computational power. The many worlds interpretation, for instance, the many worlds approaches or many history approaches to quantum mechanics. What matters is only the size of the source code, essentially. And that source code can be quite small. So many worlds survives Occam's razor. And then some physicists might say, but there are a bunch of metaphysical problems that come from that. And then they don't want to deal with these metaphysical problems and they reject the many worlds interpretation because of that. But actually, they are also resolved. These metaphysical problems, you can resolve them also via algorithmic information theory again. And one paper on that is, for instance, the title of the paper is Subjective Computable Universe by Markus Hutter, that delves into some multiverse theories and how to deal with epistemology in that. And also, for another example of algorithmic information theory being applied to metaphysics, another example is, for instance, Markus Müller's papers about physics and metaphysics and quantum theory and all that. So, yeah, I mean, you cannot reject the many worlds interpretation that easily. Some physicists will they are convinced that this is true, right? That the many worlds interpretation is true, and some are convinced that it is false. So here what I'm saying is not that it's surely true, just that you cannot like dismiss it easily. And if I would bet my money, I would actually bet it on the many worlds interpretation also, right? Without being dogmatic here. I will continue to the stagnation of fundamental theoretical physics research. So here are some quotes by Sabine Hossenfelder. She says that we are making more investments into the foundations of physics than ever, and nothing is coming out of it, and many papers are being published, and from the inside it looks like everything is going well, but actually there's really no great results. So this is not going well, and also this is the 1970s, so this is actually it has stalled for a very long time. It's half a century now. And they actually also produce many false predictions, so half a century of stagnation. And she's not the only one writing about this. There are also some other big names like Lee Smolin, who used to be the founder of or president of the Perimeter Institute, and Peter Voigt, and Alexander Unziker also wrote many books about this. And well, this is Sabine Hossenfelder's book. So it is clear that something is going wrong, but they actually all don't really know what's going wrong or how to fix it. But I will try to explain this here. So this is about resource allocation. So there are resources of various kinds. So for instance, there are a lot of papers and people don't have so much time to read so many papers, right? So how do you allocate your time resources? How do you allocate your time resources for reading papers, for contemplating ideas, for all that stuff? On the lowest level, this is kind of the microeconomic level here. And then, for instance, at the highest level, there are questions about allocating resources, such as should we fund a certain large science project, like a huge experiment, or should we fund an entire subfield or not? And things like that. Yeah, many important questions. And in between also, small organizations have to decide on which researchers to hire or fire or promote or award the prizes to. There are many decisions that they have to make, and all of them kind of influence the progress of science, right? From top to bottom here. And all of them are actually like equally important. All this is like at the top and at the bottom. At the top you have at the bottom, because it's important because there are so many of these people taking these decisions, right? And then the dean can't read, but he can count. That's a saying that captures that a little bit. So how to allocate these resources intelligently? Because this is, if there is no time to look at all of to study all of these papers, for instance, you don't know how to spend your time. You don't know which ideas are actually worth something, which ideas are worth pursuing further, and so forth, right? So then how do you actually more intelligently allocate your resources? And here there are some lessons to be learned from the optimal order problem solver paper, which is a machine learning paper, but it's not a machine learning not a machine learning talk, remember? And he has some he brings some resource allocation strategies in there in this paper and proves that these are optimal. And what he says, an important lesson I want you to take from this, is that you should allocate a significant, for instance, if you try to solve some hard problem, like for example, quantum gravity, right? Then you should allocate a significant amount of time, like maybe 50% or so, on studying on trying to incorporate solutions to smaller sub-problems, right? And per sub-problem, the amount of resources you should allocate to each of the solutions to the sub-problem should be roughly proportional to, well, the probability that it will succeed. That's bias optimality, or the probability that it will it will give you some useful insights. And to obtain these probabilities, you're supposed to use the formula that you saw earlier, which is, well, 2 to the power of the model complexity, essentially. So yeah, so you can use this. If you combine these, then you get a really powerful problem-solving strategy. And most physicists actually don't know this at all. So I will talk about how this could be fixed. So here is the like a small subproblem at the bottom, and then at the top you have the problem of finding the theory of everything. And oftentimes physicists take an approach like this where they try to solve some subproblems, but then they don't, for instance, incorporate the very smallest subproblems. At the bottom you might have, for instance, very small subproblems like find the simplest model for some small symmetry, for gauge symmetry, or for Euclidean distance, or for Lorentz symmetry, or some small symmetry groups, for instance, explain how they work, and then you combine them and you get to larger and more difficult subproblems until you're all the way at the top at a theory of everything. And for each one of these nodes, actually, you should standardize each of these research problems. And the reason for that is because each node is supposed to contain, each subproblem is supposed to contain a leaderboard, like a ranking of solutions to these subproblems, ranked by their model complexity, such that you can then simply see directly that you always know what is the currently simplest solution known to any sub-problem. So you can just directly feed off of that if you're a researcher. But they don't actually have that. The physicists don't actually think like that. They don't know how to do that. So that's where this stagnation comes from, because they have to take so many decisions at all of these different levels, like economic levels, micro to macro, and there's this whole hierarchy of sub-problems, and they are not taking advantage of the optimal problem-solving strategy at all. But maybe a physicist is gonna say, but actually we do use Occam's razor. But I will get to that later. The Occam's razor that they're currently using is actually not good enough. So I will get that, how to actually fix that, how to do it better later.
Can I ask a question on the previous slide?
Yeah, this one? Which one?
Yeah, this one. Yep. It's this, I like this framing of the resource allocation problem, and it also occurs to me that the coordination and standardization problem is perhaps even, like, in some sense more complex than the resource allocation problem, because the resource allocation, sort of once you've solved this coordination and standardization, that those challenges that you outline when you have this
Yeah,
slide
I
fully
will get to that.
populated,
So
it kind
I'll
of,
get to
then the
that.
resources sort of fall out from that
Yeah,
almost.
I will get to it.
Okay.
Basically,
Okay.
the way it works is simply, actually, there's already a good example of how to do this, which is experimental fundamental physics. And what they do in experimental physics is actually they always report their statistical significance, right? When they get some experimental insights in their papers, they report statistical significances, which, by the way, was not invented by a physicist, but physicists in experimental physics, they actually do use that. They report that, and that's why the experimental sciences, they are highly successful, and that's very scalable, because you can immediately see, based on these numbers, very efficiently, you can see whether a paper is worth reading or not, based on, or whether it's worth really drilling down on something based on just like how much statistical significance there is, right? But on the other side, on here, direct side-by-side comparison in the theoretical sciences, or at least theoretical fundamental physics, they actually don't calculate and report their theoretical significance, because they actually were never taught that. And that's where this whole failure comes from. But the theoretical significance, essentially what this is just you have to report the model complexities. You're supposed to calculate how complicated is your model. If you invent a new model, yeah, that's what you have to do. Just like on the other side, they report statistical significances. You're supposed to report model complexities, which And imagine if the experimentalists would not have been reporting statistical significances, then it would be a disaster. And that's the reason why they actually do that all the time, right? They report this all the time. So that's how the resource allocation would become much more efficient, much smarter after they would actually start doing that. And now, well, how do you actually calculate model complexities? And I mentioned earlier that actually physicists, they were using Occam's razor, but just not correctly. And here is an example of how not to do it, right? Minimize number of postulates. That's how they used to do it. For instance, just how many philosophical postulates do I start from? But that's very inaccurate. It's not going to work because a postulate can carry an arbitrary amount of information. So it's highly inaccurate. So you could have a postulate containing a huge amount of information or little amount of information, but the amount of information is actually what matters there, right? So that doesn't work. And beautiful math. So judging simplicity by just like doing a superficial judgment of simplicity also doesn't work. I think we mentioned this. I mentioned this earlier, right? We talked about this. So there's also a bunch of hidden complexity in all your mathematical definitions, especially if you have a mathematical model made of some traditional mathematics and all that. So you would have to also take all of that into account. So that also doesn't work. And there's also a whole book by Sabine Hossenfelder about how this superficial kind of beauty or elegance, simplicity of mathematical formula is not good enough, or it led oftentimes to people just getting lost in mathematics. And I will get to how to do it better than this. But first, actually, sometimes in the past, this actually has worked out correctly. And the reason for that, that it has actually worked in the past some of the time, not all of the time, is that beauty also has something to do with simplicity, right? According to Schmidhuber's theory of beauty, it's correlated with how superficially compressible something is, and then that's, well, yeah. If you want to know more, you can just read Schmidhuber's papers about beauty. But I will continue to the third method that also doesn't work, which is just people using some kind of researchers using their instinct. There's an Occam's razor instinct, basically Bayesian instinct in the brain that you could use to make progress, but this only works if you work by yourself, and it's going to be also quite inaccurate, and you're not going to be able to convince collaborators like that, so it doesn't scale either. It also doesn't work. And then the question is, well, if all of these three methods are no good, then how do you actually calculate the model complexities and report them? And I should also mention at this point that model complexity is a term from machine learning, and also that has led machine learning to great success, that the machine learning algorithms, they're constantly minimizing model complexity in the background. But this is not a machine learning talk, right? But are you still here also? Do you have anything you want to say, or okay? So I will now get to how to actually calculate the model complexity. So in principle, you could do it all so by pen and paper, but I will say that this should all be automated nowadays, of course. You could essentially, the way it works is like a compiler. You start from some kind of mathematical formula that you want to publish. So for instance, here we have the Einstein-Hilbert action as an example, and then you would type the formula into some computer algebra system, such as Wolfram Alpha, but some other system, and then that would translate it into, it would access the Lean math library, which is also used by the greatest living mathematician, apparently. So in that math library, it would look up all of the definitions that are required. So for example, up there you have an integral. So it would look up the definition for an integral and various other definitions that this is based on, right? So then it would use all of that to calculate the complete complexity from bottom to top, starting, from the definitions of like predicate logic and set theory and the foundations of mathematics and so forth, all the way up to your formula. So then you know all of that. Then you know the total amount of hidden information behind your formula. And then you should report this actually. So, and also, of course, that should be based on the reference formalism. Tromp's binary lambda calculus actually also tells you how to translate all of this into a binary code. And then at the end, you just have to report the length of this binary code, essentially. So what it does is it starts from this formula and it compiles it all the way down to a binary code. And then the length of that binary code, that's actually the actual model complexity. And then you have to report this model complexity in your paper if you want to publish a new model, right? That's how it's supposed to work. And that's how you would not stagnate. That's just like if you would be reporting statistical significance, right? In analogy. And alternatively, if you have something like what the Wolfram Institute is doing, like these Wolfram hypergraph rewriting models, you don't have to go through all of this mathematical steps in between. You could just directly compile it down into lambda calculus and get the binary code and report the model complexity like that. Is it fair if you skip this? Because that allows you to have much simpler models, right? If you can skip all these intermediate steps. Well, yeah, it is fair because, of course, if you use something like hypergraph rewriting, you also are not, you don't have all of the tools available. Like you're not allowed to just, or you're not maybe not going to use an integral. So it's much more bare bones, much more difficult to get any realistic physics out of that. So, of course, if you manage to recreate physics from hypergraph rewriting, from just simple rules like that, that would be, of course, much more impressive because you started from almost nothing, right? So it is actually fair, yeah. So that's the methodology. And here is Occam's razor again, and I'm gonna show again that everything was basically vague, unclear, but actually everything, in reality, everything of this, all of this is known. So for instance, which entities, these are just how many bits of information that your model is made of. And for why this is true, there exists a general mathematical proof. You can find it in my paper, and some other people also have, of course, also argued this before. They just have not explained it well enough, and I had to piece it all together. So for how to objectively count them, that's pretty much the previous slide. You can go through metamathematics and lambda calculus, like I've argued for a long time before. And how much necessity, that's basically the log minus log probability of the probability that your model is going to produce the correct prediction. But that's a detail you can find in my paper in the generalization to stochastic models. The argument I showed earlier, the democracy of the deterministic, the democracy of the complex models is actually the democracy of deterministic models. But in my paper, you can also see that how to generalize that to stochastic models. And there I also explain a bit about the necessity, the cross entropy loss, the empirical loss. These are machine learning terms, by the way. And how to make it scalable, I also showed that. For efficient large-scale collaboration, standardize many research problems, and for each sub-problem separately, keep on ranking solutions by their model complexity, right? And then the people that are higher up, the people that are working on sub-problems that are higher up in the hierarchy, so kind of larger problems, they can then feed off of the rankings of the smaller sub-problems, and that's how they can they could speed up their research by orders of magnitude. But of course, it is quite a lot of work to standardize all of this, and also to compile, to write a compiler for this is a bit of work. And then a few people should actually probably work together, such as algorithmic information theorists, people that know the lean math library, people that are good with lambda calculus, meta scientists, meta mathematicians, and fundamental theoretical physicists. They should all sit together, some of them, and then they should get all of this done, standardize some of these research problems, and also standardize how to calculate and report model complexities. And then by doing that, you could actually end the stagnation of theoretical fundamental physics, or at least, to put in a little bit more nuance here, if you believed that the probability of succeeding is non-negligible, then maybe now you should think that the probability of succeeding is at least plausible with the new methodology. And if you thought it was previously only thought it was somewhat plausible but not likely, maybe you should think that it's likely to succeed now. And if you thought that since physics has already stagnated for half a century, it will stagnate for another half century, maybe not. Maybe it will only take 5 years. Who knows? Maybe whole order of magnitude faster, just like we saw with Einstein initially. Except the difference, of course, here is that with Einstein, that was only very few people, only a couple of people working together. So they didn't need to have a scalable method, like reporting model complexities. That was not necessary back then. But if you want to actually harness the brain power of an entire community, then you really need to report these model complexities, just like in the experimental sciences, statistical significances are reported, yeah. And here is, I will read a short excerpt from the end of my paper. Just, okay, who in the field of physics should be most motivated to adopt mathematical regularization? By the way, regularization is also a term from machine learning, which just means that you penalize high model complexities. So then that's kind of an implementation of Occam's razor that is always running in the background in these machine learning applications, right? But here I call it mathematical regularization because that's a kind of regularization of the whole ecosystem of fundamental theoretical physics research that uses mathematics. Okay, but I will continue reading here. I will answer this question while climbing through the levels of analysis again. Firstly, any physicist, so the people who should be motivated, right? Firstly, any physicist who believes their own models to be closer to reality than alternative models should be motivated to adopt the new methodology, since it would allow them to calculate and publish the low complexities of their own models in order to lay claim to having found the correct solution to an open problem. Next, research communities that have long been working within a promising theoretical framework should be motivated to adopt the new methodology because it would allow for the identification of the strengths and weaknesses of their own theories, conducing the import of solutions from other communities to plug the holes of their theories, thereby strengthening their own theoretical framework in the long run. Also, scientific journals should be motivated to require the new methodology for publication, as it would allow them to more easily distinguish significant papers from the many insignificant papers when deciding on which papers to publish, thereby increasing the journal's impact factor in the long run. Lastly, the same is true for large research funding agencies, as the transparency brought about by the new methodology would allow them to more accurately compare the potential merit of different research directions, enabling a smarter allocation of resources. And to summarize what we have explained overall, in fundamental theoretical physics research, the adoption of mathematical regularization as a methodological quality standard in combination with the official standardization of theoretical research subproblems could increase the chances of this field's forthcoming success by orders of magnitude. Moreover, all of this is practically and technically feasible at present. Okay, that's the end of my excerpt. And here is the bibliography. This is my paper, and these are some of the most cited people in my paper. And there are 100 plus other references, and you can also see the paper here, and you can send me emails for if you want to contribute or you have questions or suggestions or something like that. Yeah, that's the end. Thank you for your attention, and I guess let's have some discussion or questions, although I'm already a bit tired by now.
Thank you, Gabriel.
Yeah.
Yeah, so I'll start off with a question or more of a
Yeah.
comment, I guess. So, the determinism of phenomenon in our universe is sort of what fuels this, or what fuels the ability for scientific models to make predictions. Um, would you agree with that?
Yeah, but you could also have a non-deterministic model, of course.
Yeah, it could be
So as long as it
stochastic.
follows, yeah, as long as there is some regularity, yeah, sure, you can you can find these regularities and use them to make some predictions, yeah. Even though it's randomized or probabilistic or so, yeah, sure.
But yeah, so like the idea of a model being a sort of way to predict things, to say like, oh, if you have this input situation of, these components, these physical objects like in motion, and then they collide, and then I can run this calculation to know what the outcome will be. And if you do that same input setup again, then you can use the same model to predict again the output. So
Yeah.
it seems like that is to say that the model itself is an algorithm, that you have like input information going into the model and then an output going out of that model. And
Yes, correct, yeah.
and
But
so
there also exist randomized algorithms, right? So not all algorithms have to be deterministic.
right, we can
I
know
mean, or at least
probabilities.
yeah, you could have an algorithm that just outputs a probability distribution. That would be basically a probabilistic model, or you could have an algorithm that just outputs predictions, but the algorithm contains some kind of it accesses some source of randomness and then or some pseudo-random number generator also
Mhm.
possibly. So then you also get some stochastic outcome, yeah.
Yeah, so yeah, that encompasses a lot of statistical mechanics and quantum theory too, because they're dialing in what those probability distributions are and having models that calculate those distributions.
Yeah, sure, yeah. So that's all included, yeah, in this. And also different, yeah, some models are based on axioms and some other models are not based on axioms and yeah, all kinds of stuff is included in there, yeah. But do you have some concrete question or
No, just an observation. Um,
yeah?
one question that I do have regarding, um, was it the common compiled language, or you said that there was a formalism, uh,
Do you mean reference formalism?
reference formalism. Yeah, that's what you were saying. So it's like there are a lot of different uh, formal systems in which to compile a given model. And
Yeah.
you kind of honed in on lambda calculus as being the simplest formalism. Uh,
Yes.
so I guess the question is sort of on the issue of computational equivalence. If there are other equally valid formalisms to compile things into, can you speak to that?
Um, yeah, I mean there are yeah, the other things that you could compile into the other reference formalisms, I kind of went through it a bit. So, for instance, something equally simple. So, first of all, there's an argument to be made that it should be as simple as possible, right? While still being universal. If it's not universal, then it's not, then it doesn't capture all possible models. So, for instance, I mean, there exists some models of computation that are not universal. Like, I forgot what they are called, but so you're not allowed to make it too simple, but it should still be as simple as possible. There's an argument for that. And then, yeah, Trump, like I mentioned, he looked at SK calculus, for instance, because that's similarly simple to lambda calculus, but then he concluded that this is not a good reference formalism, for example. And for example, there's also Marcus Müller's approach, right, where he proved that it doesn't really work in the end. But like, let's say hypothetically, Marcus Müller's approach would have worked, uh, then it would still not be practical. So because he has like a distribution over various different reference formalisms, so that would just make it more difficult to get anything done, right? Because you would have to like take into account multiple different reference formalisms at the same time, basically. That would not be practical. So lambda calculus has the advantage also of, yeah, well, it's widely known, it's practical, it's expressive, it's simple, and so on and so forth, various. So this is like the whole thing, why to base it on lambda calculus is kind of a long list of arguments, right? Comparing it to various other reference models, reference formalisms, and also, oh yeah, there's another thing to be said also. If you have another reference formalism, let's say an alternative that is similar to lambda calculus, and you want to use that, and it's also very simple and all, the difference is not going to be too large between them, because there's the invariance theorem from algorithmic information theory. So they will actually roughly agree on the predictions. Most of the time they will actually agree. So it's not a real issue in the end. Yeah, even let's say even theoretically, if you reject lambda calculus and you want some alternative, let's say, for example, a lambda calculus that every time you do the beta reduction swaps the order of all symbols or something like that, right? That would still be kind of similar and would still be kind of simple. But ultimately, the model complexities you would get in practice, they would be kind of the same, roughly the same. So then, well, it wouldn't make too much of a difference in the end. So I hope that answers all of this. Invariance theorem, yeah. Are you still here? Okay.
Yeah, Gabriel, I have a question. Thank you so much for this presentation. I really, really like this project a lot, and you make it quite digestible for somebody like me. So I appreciate that. I think my question is, given that Occam's razor is provable, right? I'll take that as a given now. How do you account for the proliferation of complexity that we see? Because it seems to me that Occam's razor would suggest that one would expect then that we wouldn't have such a proliferation.
Yeah, actually, yeah, there is a comment I can make about that, which is that if you look at the universal prior, which is basically the probability distribution of this that comes from this mathematics that proves Occam's razor, it also says that the expectation value of the model complexity is infinite. So it doesn't tell you at all that you shouldn't expect the universe to be simple at all, first of all. And secondly, even if you have simple rules that you start out from, right? And you probably all know this from the Wolfram Institute. You can start from very simple rules. And then, like Stephen Wolfram shows in his book, you actually can get very complicated looking behaviors out of that. So, or even like a very simple, very basic example, I guess, is prime numbers. Actually, John Tromp, which I mentioned a lot, he actually calculated that, or at least the shortest program for generating the prime numbers that he found only using lambda calculus was 22 bytes. So that's quite small. But then if you look at the prime numbers, of course, they look quite random. So it looks complicated, but actually the program behind it is simple. Yeah. Or if you look at the digits of pi or something like that, there's maybe a simple algorithm that generates the digits of pi, but then the digits of pi, they themselves look kind of random. So kind of more complicated. Yeah. And yeah, that's all.
Yeah. So like they're just taking a slice out of sort of potential observation space. It just happens to look more complex, but the actual root of the observation could be elsewhere and more simple.
Yeah. So
I mean, I was also thinking about I was thinking a little bit more toward the latter part of your presentation around the cultural phenomena that drives this sort of, it provides incentives for complex explanations.
Yeah, this is all intertwined, yeah. The culture of the researchers and like what kind of methodology they use. If you
and
don't
the
have
economic incentives too. The economic incentives are quite strong to maintain kind of complex, high barriers to entry with complex explanations.
Oh, yeah, kind of, or at least to they kind of swipe maybe some problems under the carpet to some extent some open problems. Yeah. So if there is maybe some complicated explanation that they use in some approach to physics, then they will tend to not report that this is like an open problem to find a simpler explanation, maybe because that's a bit difficult and they need funding. So then they to make an approach look more an approach to physics look more make it look like it has a higher chance to produce merit, right? Then the actually large the huge problems are not necessarily reported, and then it's kind of difficult to see that if you are maybe maybe deciding who should get funding or what to study, and then other factors will drive all of these decisions instead of maybe something more based on merit, based on low model complexity, will be more about, well, who has more prestige, for example, or something like that. So yeah.
Yeah, I see that's as another strength of the framework and the approach that you're advocating for.
Yeah.
Yeah, some
more
comments
questions
from chat on YouTube. Daniel Van Zant was asking about the Poisson model for computation. I think that refers to and we talked about that. Basically, it's when things are not totally deterministic, but there's a probability distribution involved.
Yeah.
Or some sort of stochastic randomness.
Yeah, you can see it. I mean, I have some references about stuff like that in my paper in the section called Generalization to Stochastic Models. There I talk all about all these probabilistic or randomized or stochastic models. And yeah, if you want to know even more information, then you just go to the references that I listed there, and then you can see more of that stuff. Yeah.
And JN from chat is asking, what axioms and lemmas are used in this proof? Are there axioms based on aesthetics?
In my proof, I actually haven't listed. It's just I'm just using the standard kind of mathematics of algorithmic information theory. So they are just like, oh, there's someone raising their hand.
Yeah,
they are just.
I guess I can touch on this. I mean, from what I understand of your argument, it's you have there's the universe and there's phenomenon in it, and insofar as the phenomenon is repeatable or there's can be empirical science.
I think I get what the question. I think I get more now what the question was supposed to be about. Probably what they mean is like, if I applied this, if I drank my own medicine, basically, because I say they should report model complexity, right? So then the question is, should I myself also, for my proof, also kind of minimize the model complexity? And here the answer is basically no, not really, because what I do is I try to just start from reasonable assumptions. You can just go to the the assumptions. Wait, they are here. Yeah, these are just, I just start from these initial assumptions, and then I just use the mathematics that is like a bunch of theorems that are known to be true from algorithmic information theory. Yeah. So that's not the same as doing empirical science where you just like invent a model to explain observations. It's a different situation. So yeah, I don't have to here minimize the information I start, or at least if we take all of these initial assumptions, if we accept these initial assumptions, yeah. And there's also Brian Silverman who wants to say something.
Yeah, Brian, go ahead.
So it seems like one of the things that you're doing here is trying to quantify simplicity by building a lot of other work that was trying to quantify complexity, which I guess are just two pieces of the same coin.
Yeah.
The thing that I wonder is, do you think that you can actually objectively quantify simplicity in a way that works across all possible observers?
So observers of what kind? What do you mean? All possible observers?
Observers in the Wolfram physics sense and the multi-way sense that a lot of what's come out of Stephen and everybody around him's work recently is
Like
saying that we're looking at this piece of the Rulliad, but we're looking at it from a nearby piece of the Rulliad.
Okay, yeah, I haven't studied the Rulliad that much, but yeah, I
Well,
think that it's going to
because
work in general, yeah.
so it's maybe
But maybe I should say like it's there's also a distribution over, or it will be kind of like the democracy, like democracy of complicated models. So with the observers, maybe there will be also democracy, and then it will kind of work for most of these observers, and then for some very strange alien observers, it won't work. But these are
but
maybe
that's
minority, right?
maybe, and it's funny though because that's kind of a rephrasing of what I was saying. So ET shows up. Do you think ET would agree on lambda calculus as being the reference representation?
Yeah, I think so. Or it might have some um, slightly different reference formalism. Or it depends also on how much computational power it has. If it has a huge amount of, like an unlimited, if it's somehow figured out to make a computer with unlimited computational power, it might take approach like what Markus Müller tried to do to get or it might, get a distribution over many different reference formalisms that are all kind of simple, something like that, maybe.
Okay, no, because that's kind of answering it because to just play back what you just said and what you just said, the nature of the reference formalism may depend on the computational power of the observer.
Yeah, but for any practical, yeah, like we have very limited computational power. So in practice, it only makes sense to use something like the lambda calculus. And if you want to, well, use all kinds of different reference formalisms, just working with the lambda calculus alone, just that alone will already be a lot of work, right? So if you would take a distribution over all possible reference formalisms, it would just increase the amount of resources you need, and it would probably not even make too much of a difference in the end, because there's also this invariance theorem, right, that says that these reference formalisms, the reasonable reference formalisms, they will roughly agree as long as they are all like roughly simple. They will roughly agree on what the right predictions are.
Okay, well, thanks.
Okay. So one more. Hello?
Yeah, I'm trying to think. Yeah, there's so much to talk about in this. Ellie, do you have something?
I mean, I could ask another one because Gabriel, you said it's not a talk about machine learning,
Yeah.
but I also wonder how you think about these insights in the context of machine learning.
Yeah, there are many connections actually. I mean, I mentioned Solomonov, which originally developed this stuff for machine learning, and there's like pack learning, which I also mentioned, which is also machine learning. There's also optimal order problem solver that I mentioned from Jürgen Schmidhuber. And then there is also actually the meta science of machine learning, which is like how do they even organize themselves to to
Yeah, that's the
achieve as much
direction I'm
progress.
curious about.
Yeah. So how much? Yeah. How do they even organize themselves as a community to make as much progress as possible in machine learning, right?
Exactly.
Yeah, and then that's what they do there is so if we go forward to these slides about these sub problems about the stagnation and how to fix it and all that. So for instance, if we have here all of these open problems and sub problems and all that stuff, and as I said, there should be a ranking for each of these nodes, for each of these problems. And in machine learning, this basically translates to they have many data sets. So they have so-called benchmarks. So each node you can think of like as a benchmark in machine learning that they use. And then they, for each benchmark, you can find online rankings of various different machine learning algorithms and how well they performed on these benchmarks. And then other machine learning researchers, they just feed off of these rankings. They just see, oh, this other algorithm there performed really well on this data set. I should probably adopt that algorithm and improve on that to tackle some other problem somewhere else, right? So that's how they made so much progress so fast. So yeah, and then in theoretical physics, you see that they didn't do that at all, and that's why it's kind of failing. Yeah, it's not scalable the way they were doing it in physics. Yeah, but they could just learn from all of this and fix that. Yeah. Next one.
Yeah. So this works well for things that can be encoded digitally or logically, but like AI models are essentially analog or neural nets. The way the model, I mean, yeah, they use floating point numbers when they're implemented in computer hardware, but essentially it's these quantities that are being multiplied and then thresholded, added together.
And by this works well, what exactly do you mean works well? The whole
your program for you have a model, it makes a prediction.
Okay, so like the compilation down to model complexity, you mean? Like
yeah. So take the model and compile it into formal language. Take a reference formalism such as lambda calculus, and then spit out the.
Yeah. So you want to know how they calculate model complexities in machine learning?
Well,
they don't compile it. Well, they don't compile it to lambda calculus. What they do there is they take some rough approximation by what they do is simply like they take the squares of all of the weights of the neural net and they just add all of that together, and then that gives them an estimate of the model complexity of the neural net, basically. But they don't report these model complexities in their papers. What they do instead is they have algorithms. The learning algorithm already automatically tries to minimize the model complexity of that neural net, because the neural net is like a model itself, right? So they during the learning process, and I guess our brains also do this automatically during the learning process, model complexity is that the high model complexity is penalized, so there's a gradient pushing towards lower model complexity, and they're also at the same time using back propagation to minimize the prediction error or the so-called empirical loss, right? So this cross entropy. And then what they do for the optimizer is they just add the model complexity to the empirical loss together, and they call this the regularized loss. So that's regularization, right? And here, that's why I call this meta-mathematical regularization here of fundamental
their
theoretical
measure for
physics
their
research.
model complexity, you said, is like the sum of the weights or the sum of the squares of the weights. So like the absolute value.
But
I
you
guess
don't have to do this like this in physics, right? It's just in neural nets, yeah.
The neural net. So like there's an argument to be made for, like, you have a graph. All these neurons are in a graph network. Together. And you could, there are sort of graph theoretic approaches to measuring how complicated a certain graph is.
That actually also, if you do that, so you mean like you want to also minimize the model complexity, not just of the like the weights, but also like the whole topology of the neural net or something like that?
Yeah, topological argument. And
Yes.
a heuristic there would be, the smaller number of neurons and the smaller number of connections between them. If you have a smaller model, graph theoretically, that does the same token prediction as a different model, then you should go with the smaller one. So it's just another way to say, like, Occam's razor, do this program, but for like analog objects that might be graphs.
Okay, yeah, there is there are graph neural networks, and there's also something called AutoML, automated machine learning, where it also tries to just well, figure out the topology of the neural net automatically without you having to like set up the whole neural net. And then yeah, so that would also, I'm sure they also use that. They just need to use a more complicated measure of model complexity, basically. Yeah. But now we are already in like talking about machine learning, basically. But I didn't want I mean, my background is AI, but I didn't really want to talk about all of this AI stuff.
Mm-hmm.
So yeah, what this talk was about is just like taking a bunch of insights that we have in machine learning, and then or even theoretical computer science and theoretical machine learning, all that stuff, and enhancing the methodology of physicists in a significant way. Yeah, that's what the talk is about.
Yeah,
But
absolutely.
are there more? Yeah, are there some more questions?
Brian, Ellie, Max?
About
No.
computational irreducibility, maybe something?
No, I'm okay.
Well, Gabriel, thank you very much for this. I mean, this was very enlightening. It gives a formally rigorous way to say, given a model, let's talk about how complex it is, actually,
Yeah.
when compiled into a reference formalism.
Yeah, and also reported in the papers and speeding up the research and everything.
Mm-hmm.
And I should also mention that the Wolfram Institute, of course, is very well suited to turn something like this into reality, right? Because you are actually, all of these people that you have that I have on the slide here, I think that you have them in the Wolfram Institute, right? You do have a huge amount of knowledge about metamathematics and physics and computer science and all that stuff. So actually you could make this happen.
Right. So yeah, we talk about computation all the time, complexity of algorithms, and reproducibility in physics. So
Yeah,
this is right up our alley. I want to thank you again for coming on. And
yeah, thank you too for having me.
Absolutely. Want to thank everyone for tuning in on the live stream. We'll see you again next time.
Goodbye.